Okay, let's finish up our discussion of scene graphs by looking at a couple of real scene graphs, and I'll show you an example of 3JS at the end. So what I want to do is go through some of the history of how scene graphs came about, the real ones that you actually see, and one that we'll actually show you. But I also want to talk a little bit about how scene graphs get rendered because it's actually can be a much more complex problem than we've dealt with before because you can be dealing with a massive database that has to be rendered. Okay, so let's start with this. Go back to something we talked a little bit about in the last lecture. That OpenGL was really aimed at people who wanted to be close to the hardware. Its original creation was to allow people to use the SGI hardware pipeline, and so it was always been close to the hardware. The word that's used, it exposes the hardware to your software. So it was of interest to people who want to do real-time graphics, who do animation, who do simulation, who do interactive applications. And important for this discussion is that generally when you use OpenGL, you're working in a standalone environment. And in a way, even when we work with WebGL and we're working with something that's running over the web, we're still running it on a single machine using data that not necessarily with WebGL, but generally comes from just that one machine. So essentially you're in some sort of a standalone environment. Now contrast that to what happens with people who are working in the CAD community. And the CAD community can be anywhere from the people who are generating animations, when they're actually designing the characters and designing the scenes. But people who are working, especially who were involved in this, were people working in mechanical CAD applications in the auto industry, the aerospace industry. So these people didn't compare, really need to use real time that much. They could often get away with doing simple models up on the display and design, but the real thing was to get a piece of a complex model, and you might have many people working on that model. So you needed to deal with very large databases that might be distributed over multiple systems. You had all kinds of the standard database issues. What happens if two people are working on the same data? So all of that was a concern to people in this community. And also you had people that were working on different architectures. You had people who were working on SGI workstations. You had people who were working under Windows. And how did you get compatibility across platforms, which wasn't a problem with standard OpenGL, because if you worked on a different platform, you would just recompile your application. You weren't worried about it working across multiple platforms at the same time. So the first real standard that came out in this direction was FIGS. That stood for Programmers Hierarchical Interface to Graphic Systems. So it had sort of everything there. It had hierarchy in it. It had programmability. It had interactivity. But realistically, what it was concerned with was, because it came from the CAD community, was how did you deal with these database issues. So they were fairly well developed within the original FIGS, and the interactive real-time stuff was not that well developed. So the organization in general for a scene graph that people wanted kind of looked like this. You had, what I mean by a scene graph here is you have a program that describes the scene. It talks to some API, and the API is built, at least we'll start with, on top of OpenGL. So you can look at it as a layer above OpenGL, and the ones we're going to be talking about today all use OpenGL for their own implementation. So not only can you write your own applications for OpenGL or WebGL, but you can write some other API that goes on top of it, and what that does is it avoids you having to deal with all of the low-level kind of issues that you have to deal with in OpenGL. So it makes it fairly straightforward often to be able to do another API on top of it. But for scene graphs, you also want to be able to use other renderers underneath. So in particular, for for the big Windows community, people still want to use DirectX, and there can be others out here. I've added the database issue in here to emphasize the point that you need some platform-independent way of storing all your data that you're generating from the scene graph. If you're dealing with some big auto design, that data should not depend on the fact that you happen underneath to be using OpenGL or DirectX, and then how it gets finally rendered and displayed while you're working on it could be through WebGL, sending it out to the web, or through OpenGL or DirectX desktop OpenGL, just going out to a local display. So this is sort of a very rough model of what we're looking at. Okay, now historically, probably the two first ones that were of interest were Open Inventor, Inventor, and then Open Inventor, and Java 3D, which had scene graphs built in. I don't know if there's anybody still out there using Inventor. There's an Inventor book within the OpenGL library. Java 3D was of interest because people wanted to do graphics with Java, and the various interfaces that people had for OpenGL, sort of a Java's version of OpenGL. They sort of work, but they never were incredibly popular. Some people still teach with a Java implementation of OpenGL, but the differences between Java and C for OpenGL can pose some significant issues. But Java 3D had, which was supported by Sun for quite a while, had the property that it did support a scene graph API, and unfortunately for people who cared about that, Sun lost interest in that, and so it's out there, but I don't think it's used very much. Now, scene graphs, also, that people who worked on that had to have some sort of file format for storing these databases, and that was standardized as both the text format and a binary format. So then you could use that and then interface, as in that figure, to various implementations, OpenGL, or generally OpenGL, or DirectX, but a lot of this stuff was implemented on special hardware, like when we had workstations, Sun workstations, and SGI workstations. Okay, now that sort of faded away, and more development happened, and we got Vermel. Vermel, the real advance here was it started to recognize the importance of the beginnings of the World Wide Web. So the idea that it needed to work with databases that might be distributed over multiple sites was part of that. And like some of the others, it was built on top of OpenGL, so that the implementers of Vermel didn't have to worry about all the low-level, how do you draw lines, how do you do polygons, all of that was automatic because it was done through OpenGL. And Vermel stood for Virtual Reality Markup Language, so it sort of fits in that whole sort of family of names with HTML, XML, and so on. Okay, now following that was around, that's maybe 20, close to 20 years now, 15 years, when Vermel was of interest to a lot of people. It was slow, and so if you try to run things with Vermel, it was nothing like the speed you would get out of just a plain OpenGL program. But that all led to OpenSceneGraph, and OpenSceneGraph is probably there's a couple out of there. There's OGL, which is different than I think it's OpenSceneGraph, and there's another one, I think it's OGL, but this has had a lot of support. It was again built primarily on top of OpenGL, but there was no reason you couldn't put another renderer underneath. I think the important part for here that we should spend a minute on is really how one goes about actually rendering a scene graph. In the last lecture, we made it kind of easy. We sort of skipped over. We said, oh, well, there's a scene.render method, and that will call the render methods of the objects inside of that scene graph. Well, it's really, what's done in a good scene graph now is much more complex than that. And a good scene graph, including Three.js that we're going to talk about in a minute, is a much more complex rendering process. And it's really a three-pass process in OpenSceneGraph and I believe in 3.js. So what happens is the first step is what's called an occlusion culling. Now, what you can do is, if you suppose you have lots and lots of geometry and you have a camera in there, and the camera is only seeing a very small part of the geometry. Now, certainly clipping will take out all of that geometry, but it can involve an awful lot of data flowing through the system before that you get down to what's actually visible in the scene. Now, one of the things you could do, and you could do this is supported in desktop OpenGL, is that, or you can write your own code to do this if you want a WebGL, is when you go through the geometry the first time, you can actually start seeing what gets rendered, or at least what appears inside of the window of the clipping volume and what doesn't. And then you could say, well, okay, these guys that aren't inside the clipping volume, I'm not going to. That's called occlusion, or things that are hidden behind something else when you're doing hidden surface removal. You could say that, oh, this surface is occluding all of this geometry that's back there. So in the first pass, you try and cull as much as you can out of the geometry, knowing by having gone through it once that a lot of it is not possibly going to be visible. And that's called occlusion culling. It's something you probably study in a second course in computer graphics. So that's one step. Get rid of as much geometry as you can. Now the second step deals with the problem of transparency and translucency. One of the things we saw when we studied that is that the order in which you render things really matters. And so in order to have this come out consistently and fit in a physically acceptable manner, you do a second pass that actually sorts the geometry so that you always do a back to front or front to back rendering. Now, both of these steps don't really use the GPU. Now, when you've done that, you've got geometry that's potentially visible. You don't have to be perfect on the occlusion pass. You just don't want to eliminate things that may be visible, but there's things you sure won't be. And you've ordered the geometry so it comes through the pipeline in a fixed way. Now you can really use the pipeline. So the third pass is through this geometry that's left, that's all been ordered, and you render it as we've been talking about before. So it's a very complex process, a lot of complex code, but on the other hand, you're dealing with some pretty massive databases in this. So if we look at one that's now very popular, if you're saying, well, if I was teaching the course still with C and C++, we'd talk more about OpenSceneGraph, but since we're dealing with WebGL, there's a very nice SceneGraph API that's built on top of OpenGL, or top of, WebGL, called 3.js. If you want to see it, and I really advise you to if you want to spend any time on SceneGraphs, go to 3js.org, download the whole thing. Got lots and lots of examples. It's all open source, lots of code, and you see what you can really do with a SceneGraph. Another thing you might do if you're really interested in SceneGraphs is look at Eric Haynes' course on Udacity. It's called Computer Graphics. And you could really see, Eric's a very good friend of mine. He has a very excellent book on real-time graphics. He's been at Autodesk for a long time. And you could see really the difference in approach to computer graphics between what you would do if you were doing a scene-based course and what you were doing if you're doing a course like ours, which is OpenGL, WebGL based and closer to the hardware. So in the 3JS world, it's really for people who want to use the geometry and work at a much higher level, and these are generally the modelers. They really like 3JS, and you can do some pretty impressive things. You still work with code, but as you'll see in my trivial little example coming up, the code is very different from the code that we've been using. In some ways it's the same, but in the modeling part, it's very different. So you might want to look at that. I actually spent some time doing a lot of my examples using 3JS's math libraries. It's got a lot of libraries in it, which in principle you could use and you may want to try. I found there are a lot of quirks to being able trying to use their libraries because they're really customized to being used with the whole package. But it's possible to use their libraries, and I have some example code if anyone wants me to send them some code with it. So here's the example I just downloaded from the web of a very simple, of their simple My First program in 3.js. And so there's, I'll show you the render loop on the next slide, but here's here's the description of a scene graph, and all you're doing in this scene graph is you're doing a rotating cube. So it's something we've done before, and you can see the difference in flavor. So you start off with this root node that comes from the three objects. So you start with a new scene. Then you say, what kind of camera do I want to use? So you're saying I want perspective here. Here's the standard parameters for the camera that are based on the size of the window. That I'm leaving that HTML stuff out of this, but it's based on what camera, the canvas that you created. You decide what kind of render you're going to. So 3 is very powerful in the sense that it can render in different environments. So you say, I want to use the WebGL renderer. Then you set what size window and height you want to do. There's you append this to the to your display. So you want to the document what you're displaying. You're going to append this onto it. So this is just sort of setup stuff. Here's the geometry. You're saying I want a cube, and the cube, the material is really, it's a mesh. Okay, so there's certain standards built in. It's saying I'm going to use a mesh material for it, and the color is it's 2 hex characters for red, 2 for green, 2 for blue. So this is full green, no red, and no blue. I'm saying the cube is using a mesh with the geometry I defined up here, which is just say I want a cube, and with this material that I defined over here, and then I add it to the cube, and now I'm going to also back the camera away from it because this is putting the cube at the origin, so I'm going to move my Z back a bit over to Z equals 5. So I think it's pretty clear what's going on here to set that up, and compared to what we had before, there's some pluses and minuses here. One is the cube is already defined. It's in there. You simply use it. You get to use different renderers. This is a little flaky in here because, as you'll see when I show you the thing, you're coloring the whole cube green, which doesn't really give you a very nice view. However, putting in more complex materials and just involves just setting a bunch of properties for different materials here. Look at those examples if you're interested. And finally, okay, now I've set up my scene. What does the render loop look like? Well, this should look fairly similar. The renderer calls itself, so you have a render you start the render, but the render function calls itself, so essentially you're requesting an animation frame of render. You use the renderer that you set up before. That's the renderer for WebGL. You pass it the scene, you pass it the camera, and now there's your standard render loop with that camera. If you want to change some properties, you can just change the properties dynamically of the camera. Here's the rotation. You're just rotating about both the X and the Y axes. This is rotation about X, rotation about Y. You're incrementing the angle by 0.1. I think this is in radians. I'm pretty sure this is in radians, by 0.1 radians each time. That's it. I mean, so here's a very simple 3 example. Here's let me show you the renderer and the rendering here. Here it is spinning around. This is pretty ugly because there's no lighting or shading going on here. It's just coloring everything green, so you don't really see the cube very well. On the other hand, the program is pretty simple. So that's about, basically all I really wanted to say about scene graphs. We could spend weeks going through the details of scene graphs, but I think the important thing here is that to see where our approach to computer graphics, which is much more, I think, appropriate for a computer science, computer engineering class is, and this is pretty much the material you would study in any place else where you took a computer graphics class, at least in CS or computer engineering, versus what you might study if you were, say, doing a CAD course in a mechanical engineering department.